TPM in Windows Hello Complete Interaction Flow. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Understanding how the Trusted Platform module interacts with Windows Hello requires examining the complete lifecycle from initial enrollment through daily authentication. The TPM serves as the hardware security anchor that makes Windows Hello's passwordless authentication both secure and practical. Let me walk you through each step in detail, explaining exactly what happens at every stage of the process. The first sequence diagram illustrates the enrollment phase where Windows Hello is initially set up on a device. This process begins when a user decides to configure Windows Hello for the first time. The Windows Hello service first communicates with the TPM to verify its presence and readiness. The TPM must be version 2.0, enabled in the BIOS, initialized, and owned by the operating system. Once these checks pass, Windows Hello instructs the TPM to generate an asymmetric RSA key pair, typically 2048 bits in length. This is a critical step because the key generation happens entirely within the TPM hardware, and the private key is generated in such a way that it can never be extracted from the TPM, even by privileged system administrators or sophisticated malware. The private key remains permanently sealed within the TPM's secure storage, protected by hardware-based access controls. The public key, however, is extracted and sent to the identity provider, which could be Azure Active Directory for cloud-joined devices, on-premises Active Directory for domain-joined devices using certificate-based trust, or Microsoft Account Services for consumer scenarios. The identity provider registers this public key and associates it with the user's account. From this point forward, the public key serves as the unique identifier for this specific device and user combination. No other device can impersonate this registration because they would need the corresponding private key, which exists only in this device's TPM. Next, the user creates their Windows Hello credential, which can be either a PIN or a biometric sample. For PIN creation, the user enters their desired PIN through the Windows Hello interface. This PIN is immediately hashed using a one-way cryptographic function, and only the hash is stored, never the plaintext PIN. The PIN hash is stored within the TPM's non-volatile memory in a protected storage area that is tied to the private key. This binding means the PIN can only be verified by the TPM that holds the corresponding private key, reinforcing the device-specific nature of Windows Hello credentials. For biometric enrollment, whether facial recognition or fingerprint scanning, the process captures multiple biometric samples to create a comprehensive template. For facial recognition, the infrared camera captures the user's face from multiple angles and under different expressions, building a three-dimensional model of facial geometry. This model is converted into a mathematical template using proprietary algorithms that extract unique facial features while discarding the actual image data. The template is a one-way representation, meaning you cannot reconstruct the original face from the template. Similarly, fingerprint enrollment captures multiple fingerprint impressions, extracts minutiae points and ridge patterns, and converts them into a mathematical template. These biometric templates are encrypted and stored in the TPM's protected storage, isolated from the operating system and applications. The raw biometric data, such as the actual photos or fingerprint images, is never stored anywhere and is discarded immediately after template creation. The second sequence diagram shows the authentication flow that occurs every time a user signs into their device. This process demonstrates how the TPM, Windows Hello, and the identity provider work together to authenticate the user without ever transmitting passwords or biometric data over the network. When the user approaches their device, they interact with the Windows Hello credential provider, which is the login screen component that prompts for authentication. If using biometrics, the user presents their face to the camera or finger to the sensor. The biometric sensor captures the current biometric sample and immediately compares it against the stored template locally on the device. This comparison happens in the Windows Hello service and never involves network communication. The biometric data is captured, processed, compared, and then immediately discarded, all within milliseconds and all on the local device. If using a PIN, the user enters their PIN on the credential provider screen. The entered PIN is hashed using the same one-way function used during enrollment and sent to the TPM for verification. The TPM compares the hash of the entered PIN against the stored PIN hash in its protected memory. If using biometrics and the biometric comparison succeeds, or if using a PIN and the PIN hash matches, Windows Hello then instructs the TPM to unlock access to the private key. This is the critical step. The private key itself never leaves the TPM, but the TPM is now willing to use that private key to perform cryptographic operations on behalf of the authenticated user. At this point, the authentication process transitions from local verification to proving identity to the remote identity provider. The identity provider, whether Azure AD or on-premises AD, sends an authentication challenge to the device. This challenge is a cryptographic nonce, which is a random number used once to prevent replay attacks. The Windows Hello service receives this challenge and passes it to the TPM along with the request to sign the challenge using the private key. The TPM, having already verified the user's PIN or biometric, uses the private key to create a digital signature of the challenge. This signature can only be created by the private key, and critically, the private key never leaves the TPM hardware during this process. The TPM returns the signed challenge to Windows Hello, which then sends it back to the identity provider. The identity provider receives the signed challenge and uses the public key that was registered during enrollment to verify the signature. Public key cryptography ensures that if the signature can be verified with the public key, it must have been created with the corresponding private key. Since the identity provider trusts that the private key is secured in the TPM and can only be accessed after successful local authentication, verifying the signature proves both that the user successfully authenticated locally and that the authentication is happening on the registered device. The identity provider then issues authentication tokens, such as OAuth access tokens and refresh tokens, that grant the user access to resources. These tokens are returned to the device, cached for single sign-on purposes, and used to access applications and services without requiring repeated authentication. The third sequence diagram illustrates a critical security feature: TPM anti-hammering protection against brute force PIN attacks. This protection is essential because PINs can be shorter and simpler than traditional passwords, relying on the hardware protection rather than complexity for security. When a user enters an incorrect PIN, Windows Hello sends the PIN hash to the TPM for verification. The TPM compares the hash against the stored correct PIN hash and determines that they do not match. At this point, the TPM increments an internal counter that tracks consecutive failed authentication attempts. This counter is maintained in the TPM's secure storage and cannot be reset or manipulated by software. If the failure count exceeds a configured threshold, typically around 5 to 10 failed attempts depending on TPM configuration, the TPM enters a lockout mode. In basic lockout mode, the TPM begins enforcing increasing time delays between authentication attempts. The first few failures might have minimal delay, but as failures accumulate, the delays grow exponentially. After 10 failed attempts, the delay might be several minutes. After 20 failures, the delay could extend to hours. This exponential backoff makes brute force attacks computationally infeasible because an attacker attempting all 6-digit PIN combinations would require years to complete even with physical access to the device. In more severe cases, if the failure count reaches a critical threshold, the TPM may enter full lockout mode where it completely refuses authentication attempts until an administrator intervenes. The lockout can be cleared through TPM owner authorization, which requires administrative credentials and often physical access to the device. Some organizations configure policies that automatically wipe the TPM after excessive failed attempts, which would delete all Windows Hello credentials and require complete re-enrollment. This provides strong protection against stolen devices being compromised through PIN brute force attacks. When a user finally enters the correct PIN, the TPM verifies the hash match, resets the failure counter to 0, and proceeds with the normal authentication flow, unlocking the private key for cryptographic operations. The security model demonstrated in these diagrams is fundamentally different from password-based authentication. In traditional password authentication, the password is transmitted to the authentication server, which compares it against a stored password hash or validates it against a directory. This transmission creates opportunities for interception through network sniffing, man-in-the-middle attacks, or server compromise. With Windows Hello and TPM, the PIN or biometric never leaves the device. The private key never leaves the TPM. Only public key signatures are transmitted, and these signatures are useless to attackers because they are valid only for the specific challenge they signed and cannot be replayed for future authentication attempts. The hardware-based protection provided by the TPM means that even if malware gains administrative privileges on the device, it cannot extract the Windows Hello private key or the biometric templates. The TPM's hardware isolation ensures that these secrets remain protected by silicon-level security mechanisms that software cannot bypass. This is why Windows Hello with TPM provides such strong security properties and why it is suitable for high-security environments including government agencies, financial institutions, and healthcare organizations that handle sensitive data and face sophisticated threats. Organizations deploying Windows Hello should ensure that all devices have TPM 2.0 enabled and properly configured. BIOS settings should be verified to confirm TPM is enabled and activated. Device provisioning processes should include TPM initialization as a standard step. Users should be educated about the security benefits of Windows Hello and encouraged to enroll biometric credentials for the best user experience. IT support teams should be prepared to handle TPM lockout scenarios and have clear procedures for PIN reset and re-enrollment when necessary. By understanding the detailed interaction between TPM and Windows Hello shown in these sequence diagrams, administrators can better support users, troubleshoot issues, and appreciate the robust security architecture protecting their organization's identity infrastructure. Thank you for your attendance. Please consider subscribing to the channel and liking this video.